of the soil. Okay. We are probably also looking to reduce settlement that might occur. So that is, in other words, improving the stiffness of the host soil. So that's a serviceability limit state type application. Now, often it's actually settlement that drives ground improvement, although bearing capacity, of course, always remains important. It could also be things like reducing the permeability of the ground through groundwater control. It could be liquefaction mitigation, but we won't really be going into that here. So our main focus when we get to rigid inclusions will be settlement and bearing capacity. And these are just sort of techniques that sort of describe or show a little bit the huge spectrum of different ground improvement techniques that are available. So, you know, everything from dynamic compaction, or I think this is probably what I'll call dynamic replacement, to compress the soil, improve its stiffness and bearing capacity. This is jet grouting, which is also considered as a ground improvement technique. Very versatile in the right conditions and used a lot in tunneling and groundwater control. This here is what I would call a vibraplot or a depth vibrator that's being used by the looks of it to do vibro compaction in some granular material there. So there's a vast spectrum of different ground improvement techniques. Now, obviously in Europe, we are using Eurocode 7 now, and there's a second generation of the Eurocodes, structural design standards, coming out, and really for the first time, ground improvement is being considered in Eurocode 7, and they've divided all these different techniques up into sort of 4 broad categories. So firstly, they are looking at diffused and discrete. Now, diffused means the technique is, well, it's probably easier to describe discrete. So a discrete technique is something that is installing something that is, as it says, discrete. So it could be a stone column, which of course is something that is separate from the surrounding ground but put in it. And it could be rigid inclusions, which are usually concrete, but could be other things. So those are discrete. So you can actually point to a stone column or a rigid inclusion and say that's what that is. Diffused is sort of everything else. Okay, and then you've got 2 different classes here. So there's class 1 where you're not really creating something with an unconfined compressive strength. So, for example, dynamic compaction, you're just compressing the soil, but it's not creating any compressive strength. Whereas if you were doing, say, grouting or permeation grouting, so that's where the grout flows through the pores of the ground, it's diffused, but you are creating something that you could measure an unconfined compressive strength. Discrete, again, could be stone columns, and again, you're not creating something that's rigid and has an unconfined compressive strength, but you are improving the general stiffness of the soil. And finally, and this is where rigid inclusions come, you've got a discrete technique where you are in fact creating something that has an unconfined compressive strength. And this is just some photographs of some exhumed columns. I think some of them might be jet ground. It wasn't entirely clear, but this and the soil has been moved from between them, so you can see that they are discrete items, and you could take some cores and do strength testing. So this is again the overall kind of world in which we're living, the ground improvement world. And for rigid inclusions, we're in this box here. So as I say, they are discrete. The strength of the column is significantly greater than the strength of the host soil, and the stiffness of the column is significantly stiffer than the stiffness of the host soil. But, and we'll go into this in a bit more detail in a minute, they do act very much together. The column acts very much together with the host soil. Now, what we should be aware of, and I think it's very important to consider rigid inclusions as a system or a philosophy of the ground, a load transfer layer, and the foundation of the structure, or it could be an embankment, all working together. Okay, so and with rigid inclusions, some consider them a new ground improvement process. And as I said before, I think they've reached a tipping point in many countries where the technique really is being used more and more. I think it's fair to say that technique was really promoted by the French company Menard. And for a long time, they were driving forward the innovation. And then other French contractors became interested and started taking up the technique. But now that has spread to other countries and to a far wider range of specialist contractors. So I think now is a good time to become more aware of it, and I think you'll see more and more rigid inclusion projects going forward. And the reasons that the technique is popular is that it's often a far cheaper technique than piling. The innovations have principally been driven through specialist contractors and their marketing and promotion of the technique. The design is backed by research and experience, and we'll talk a bit about that a bit more in a minute. And I think the fact that the design of ground improvement and accommodating the design of rigid inclusions in the new generation of Eurocodes that will be coming out, and I think Eurocode 7, so that's EN 1997 Part 3, which will cover the design of specific techniques, which will probably be published in around about 2025, 2026, will cover the technique. So I think that demonstrates that it's sort of coming of age. But, and I think there's always a big but with rigid inclusions more than other techniques that we are familiar with in geotechnical engineering, with the possible exception of grouting. The components for a successful implementation or execution are that you've got to have the suitable ground conditions, you've got to have the suitable plant, and you've got to have the suitable design method. Now, I suppose that goes for anything, but it particularly goes for rigid inclusions. So, what are rigid inclusions? Well, it's quite a general term, but it is something that is a lot stiffer than the host soil. It predominantly would be a concrete column, but not always. And typically, you might be in the range 300 millimeters to 450 millimeters, but you can easily go up to 500-600 millimeter diameter, and there have been various versions greater diameter. You can create the column using different methods. So a very popular method is a rotary displacement system, but you could also use preform methods. And I've got an example where precast concrete piles were used as a rigid inclusion, but you can use steel tubes and anything really that's stiff or strong enough. You can install using different techniques as well. So this is a vibrated tube approach. And of course, if you're using something like precast piles, you might just simply drive them in the standard sort of precast piling way. The columns are usually unreinforced, except where there are either lateral or transverse loads, and certainly care is needed beneath the edges of embankments. But they are typically, if they're a rotary displacement column, unreinforced. And as I've said, they do require this composite design philosophy. So where might they fit in? So this is just a little graphic. And what we're showing here is the spectrum of strength of a cohesive soil, which might go down to as low as 5 kPa and drain shear strength, all the way up. I've gone only as far as about a stiff consistency of 100 kPa. Well, obviously piles could be used in any of these conditions. Now, vibrostone columns, which I suspect most people are familiar with, you might typically use them in the sort of range 20 to maybe 60, 70 kPa. Once you get above that, you might find you've got to pre-bore. You can still construct a stone column, but you might have to pre-bore and pre-form a hole. And at the soft end, you start to need to use stone columns with a lot of care because they do rely on some confinement from the ground around the column. And this NHBC limit, now this is a UK standard vibrostone columns for housing, and you can use it up to 30 kPa. So that's your stone columns. You might use something else like dry soil mixing, which would be very soft ground. Now, rigid inclusions, you might then fit them in between anything that is really very soft up probably to about 50 kPa, because, as I said, usually you'd be trying to use a rotary displacement system. So you've got to be able to get the tooling into the ground. But of course, you could create using other techniques. And if you've got very powerful rigs, you could be using them at the firm to stiff range. Although, of course, if the ground is good, you probably don't need to improve it in the first place, so we don't really need to go up there. So that's where rigid inclusions might typically fit in. And loading capacity, so if you are doing, say, floor slabs to a building, and you're principally looking at settlement control, the loading on the floor slab anywhere between 50 and 125 kPa might be typical. For isolated foundations, you might get a bearing capacity of 100 to even 300 kPa with the improvement with rigid inclusions. And other structures and tanks, embankments, you might even go up as far as improving the bearing capacity up to 300 kPa in the right conditions. And it's all obviously very much ground condition dependent. So how do rigid inclusions work? Well, let's just consider for a minute the case of just a simple raft foundation sitting on the ground. Obviously, 100% of the load that comes from that foundation goes into the ground. You haven't got any piles, so you've got no load going into a pile. with a traditionally designed pile foundation, the situation is reversed. So you assume that no load goes into the ground and all of the load goes into the pile. Then you have the mixed foundation or a piled raft foundation, which is entirely feasible, but tends not to be used that much apart from in more specific situations where you're allowing the ground between piles, and we're still considering these as piles, to take some load, and the remaining of the load, the remainder of the load goes into the pile. So you do have a composite system, but it's the foundation is in contact directly with the ground. Now, rigid inclusions are a further development where you've got your footing, but now in most cases, you have this load transfer layer. And we'll talk a lot about this as we go through, but this is usually a granular layer that is put above the soil surface. And the yellow here is the natural ground where the inclusion is formed. This is the rigid inclusion. So that the rigid inclusion isn't connected to the foundation, unlike, say, a mixed foundation where you would have a connection. And one of the aspects that we spend a lot of time thinking about in design is how loads are transferred through this load transfer platform in partly to the column or in to the ground. Now, this little image does show an enlarged head on the column, which you can have, but very often the columns would just be of uniform diameter. So to look at this a little bit more, now we're only going to be using rigid inclusions where we've got some soft or compressible soil layer. And if we take the case of a floor slab, which is probably easiest to demonstrate the principles, but it could be a foundation. We have the floor slab up here, and in due course, we'll have some sort of load applied to that floor slab. We have then this load transfer platform, LTP, which is usually a well-compacted granular layer that's put above the natural soil. And we get an arching effect set up within that load transfer layer so that some of the load goes into the column and some of the load goes onto the soil. Now, because this is soft and compressible soil, the load that goes on the soil between the columns causes this soil to compress and settle. Okay, and within this zone here, where this soil is settling, it's settling more than the column is settling. So there is a differential in settlement between the column, which is founded in some sort of firm founding layer, so it can't settle, and the soil next to it, which causes a down drag effect and causes load to be attracted into the column over this upper part. Now, as we go down in depth through the soft layer, obviously the settlement within that layer is going to decrease because we get near the bottom. And at some point, there will be a plane, which we call the neutral plane, where the settlement of the soil here is exactly equal to the settlement of the column. Now, at that point, there is no load transfer because there's no differential movement. And below the neutral plane, the column now is settling more than the soil. So it is generating, the column is generating now a resistance and shedding load off into, into the ground. So now when we do our design, we've got to consider how the load path and where the loads and forces are going through this system. So it becomes quite a complex series of calculations and verifications that we need to do. Okay. I would say, Tahir, are there any questions at this point?
No, we don't have any questions yet.
Okay. Okay. So now just looking a little bit more at the stress distribution through the load transfer platform. This is showing the arching the arching concept in 2D. Various analyses, these are numerical simulations have been done which show this arching effect. And of course, rigid inclusions are not a 2D problem, they are truly a 3D problem. So we can see these stress paths here showing load getting attracted to the heads of columns. And this is, again, a visualization looking on plan. So you've got a column in each, or a quarter of a column, I suppose, in each corner of this square. And you see that you've got a stress concentration going on over the column. And though there is some stress going into the ground between, it is less. Okay, and this is looking at a fairly thin load transfer platform, and this is the situation which is slightly more applicable to an embankment type situation, where the stress difference is somewhat less. So this is a slice through the surface of that, and there you've got some stress concentration on the surface. It's much less. Okay. Now the other thing you've got to recognize is that essentially the arching effect means that within the support zone you're collecting load, but you're not collecting load from there, and that can become important later on when we start talking about slabs and embankments. So some people think rigid inclusions are a new technique, but they're not. Wooden piles have been driven and sand layers placed above them. That's been found in even archaeological investigations. One of the earliest cited examples is in 69, so what's that, 50 something years ago, where a couple of very innovative ideas were tried. There's this kind of overlapping exercise where you had piles in a resistant layer and then terminated here, and the piles from the building in there, and there was load transfer there. It looks quite complicated. That was then evolved into the situation where you just had the single column, but there was no connection between the top of the column and the building. That was further developed over the next decade or so for railways in Japan and for road embankments. Then Brom's, who obviously did a lot of work on pile groups and lateral loading of piles and what have you, did some work in Sweden looking at a pile. He called them piles, I think, but on like an expanded cap. Then another example was tried or published in 1982 in Indonesia, and this is where this nearly 10-meter reinforced soil wall was supported on. In this case, they were steel tubes, but there was a 1-meter platform between the top of the tube and the head of the tube and the structure. So that really was very much like what we consider as a modern day rigid inclusion type solution.
Doctor, I have a question which you would,
yes.
I think you would like to answer it at this point.
Yeah. Okay.
It's from Suhail Kibriya, is a very experienced geotechnical engineer. He's asking, upper soft ground will have a tendency of developing negative skin friction on the rigid inclusion. How is
Yes.
this accounted for in the design?
Okay.
If you want to answer now, okay. Otherwise, you can answer it later.
Yes. Okay. So I think if I understand right, the question is that this material is above the neutral axis, is sinking down more than the column, and that is creating this mechanism of negative skin friction. That's absolutely correct, and I will come onto that in much more detail in a minute. Okay, so just moving on into this current century, for the Rion anti-Rion bridge in Greece, they used a very substantial rigid inclusion solution where they drove in these large 2-meter diameter open steel tubes that were gravel filled, supporting a nearly 3-meter thick gravel embankment onto which the foundations of a couple of the bridge piers were put. A very significant example. Now, a lot of these were, I call them bespoke developmental projects, and a real significant, I think, moment in the history of rigid inclusions occurred in 2011, when in France a research project called PSCE was launched. And we'll talk a lot about PSCE because they produced some guidance, which I still think is probably the best place to go for guidance on this topic. However, as I said, the draft Eurocode 7 is now available, and it will encompass the design of rigid inclusions when it's finally published, probably in a couple of years' time, which will really, I think, mark the coming of age of the technique as a fully established geotechnical method. As I've said, you can create the columns in many ways. They can be a full displacement system, like a rotary displacement system. They could use continuous flight auger piling. You could drive some sort of preformed either concrete or steel tube. You could use a driven cast in situ technique, which is what this was here for a road embankment. You could use vibratory methods, vibrated steel tubes, or even you could consider vibro concrete columns as a form of rigid inclusion. And you could use soil mixing or jet grouting to form a column. So it's a very flexible technique, ground, machinery, and situation dependent.
Dr. Egan, I'm getting more questions. There are 60 people in the audience. It has become difficult for me to manage today. So should I read out the questions, or you can see the chat? Okay.
I can't see the chat.
Okay, I'll read out. We have a question from Professor Tatiana. She's from Belarus. She is asking, does the load into rigorous inclusions depend of their stiffness, modulus of deformation, or other parameters? Would you like to answer this question? Then I have another question also, and another question also.
Okay, well, let's do the questions, and because then that might help. So yes, yes, obviously, relative stiffness of ground and inclusion is important and does affect the loads that are shared between the ground and the column. Although I would say in practice, because you're probably going to be using the columns through fairly soft ground, the difference in stiffness is going to be great. It's going to be more than 1,000 times different. That as some people do, they market their columns. There's one company that calls their columns controlled modulus columns, indicating they use a weak concrete, which has a lower stiffness than a normal concrete. But I don't think it makes much difference to the design. But technically, you're correct. Difference in stiffness is relevant.
Okay, now another question from Hazik Zahir. He's asking, since the soft soil at the top has more residual settlement than the rigid inclusions, I am assuming the soil settles. Doesn't
Yes.
this induce concentrated stresses in the upper region of rigid inclusions?
It does, and I will come and show some. I mean, you would typically, I think, you would use finite element programs to do the design, and I shall show some finite element output in a minute. And indeed, yes, you do. You get stress concentration at the head of the column. The load increases from the head to the neutral axis within the column, and then diminishes below the neutral axis, and we'll see that in a minute.
Okay, Sohail Kibra is asking, are such inclusions designed for lateral roads and moments as well?
They can be, but I think it will then usually mean that you've got to be reinforcing the column. And one of the big advantages, and I think I've just seen a comment on the relative costs. One of the advantages of the method is that the columns are installed very, very quickly because they're unreinforced. And if you're using this sort of rotary technique, you can be doing per rig, 300, 400, even up to 600 meters a shift. And you're not physically connecting the top of the column into the foundation, unlike with piles where you've got the reinforcement in the pile. You've got to break down the pile, you've got to tie the reinforcement into the foundation. So you haven't got to do any of that work. So the construction, say, of a floor slab or a foundation can go ahead as though there were no piling. So I suppose to answer the question, yes, they can be designed for lateral loads, but it becomes much more difficult and problematic.
The question asked by Mr. Ladeem, I think this we can defer to last. He's asking, how could we assess the increase in strength after a rigid inclusion? Do you want to answer this question at this stage, or we keep it for?
We'll come through and answer that in a minute.
He's asking Ghulam Rasool, if during zone load test settlement is more than permissible limit, how we will know it is clue to column settlement or ground settlement?
How will we know whether it's due to column settlement or ground settlement? Well, the system acts together, and yes, you might get a failure because you've got a defect in all the columns, so they're not working. But and I will cover validation and testing a bit later on, but you need to test and be validating the different components of the system. So if you could be sure that all the components are working properly, then if you've got excessive settlement, then it's probably a design misassessment, and you've probably not allowed for sufficient settlement to occur within the design. And of course, that could be due to a change in ground conditions. You've designed on one ground profile and you've ended up with another one.
Okay, doctor, we have a few other questions, but that can be answered later. You can please continue with your lecture. Thank you.
Okay, so Tahir, sorry, I should have asked earlier. What time would you like to finish by? Because
I have to finish by 4 o'clock.
Okay, so what time is that here? So how much longer have I got?
1 hour, 10 minutes to have.
Okay, fine, perfect. Thank you. Hopefully we won't be that long. So anyway, this slide just covers the rotary displacement auger system, and it's very popular because I say it can be used in the right ground conditions to achieve very high productions. So you have the rig here, you have the Kelly bar, which is hollow, through which the concrete is pumped. And at the bottom, you've got the tool, which has got a short helix there, which when this rotates, pulls the tool or helps to pull the tool down in the ground. You have the central part, which then is expanding the ground to create the void, which, as you are withdrawing the tool, is filled with concrete. And then you've got a reverse helix here, which is orientated in the opposite direction, which is there to try and minimize flow of soil up in this direction. It's forcing the soil back down. So it's a minimum spoil creating technique as well, which of course is popular because you don't have to then cart away and deal with the spoil. And these are just, there are very many tool types, and these are just some examples of the sort of rigs that use this method. And I say there are very many different tools that you can get for different ground conditions and different preferences. There are many proprietary names for rigid inclusions. So Menard say control modulus columns. Keller use mixed modulus columns, which actually have a stone column on the top. I don't know if you're familiar with Balfour Beatty, they use something called Pencol. There are controlled stiffness columns, but these are all really specific names for the generic concept of a rigid inclusion. So just to summarize this little section, it's important to think that the rigid inclusions are a system, a ground improvement system. Many, or they may offer savings in foundation design and can be fast to install. And there are no direct connections to foundations. So although the geotechnical contractor may see no benefit because they haven't got to be broken down and tied into reinforcement for the foundations, the overall project might benefit. A word of warning, a lot of clients might see lower cost and like that, obviously, but they won't always understand what they are getting into. Now, that when I say client, that might be the ultimate employer or project promoter, or it might be the main civil engineering contractor who sees rigid inclusions as being cheaper than piling, but they may not always understand the responsibilities that they are taking on, or the additional, I hesitate to say risks, but I will use the word risks, they may be taking on that need managing. And this is exacerbated by the fact there aren't really internationally recognized specification documents for the technique. And I'll come on to that in a minute. And part of these risks is because the design and construction of the system, so you've got a working platform to support the rig, you've got the rigid inclusions, you've got the LTP and the slab and the foundation, are probably by different entities. And this is where the risks can emerge that need to be managed. So I'm going to zip straight on to design and go through this fairly quickly. As I've mentioned, there are currently two main design standards that I am familiar with. You can get some other guidance as well. You obviously need adequate ground investigation before you start, and you're looking at strength and stiffness of soils, particularly consolidation properties. You need to identify where the founding layer is and what it is. You need to identify the groundwater and any variations in it. There have been rigid inclusion failures where the rigid inclusions have been installed, the groundwater has been lowered, increasing the effective stress and load on the column, which created more settlement than was envisaged. And of course, you need ground investigation to tell you what the ground is like, so you can decide on the correct technique. I would recommend looking at this PSCE document, which is available in French and English. It's not a perfect document, but no standard or design document is, but I think it's the most helpful and the best that there is at the moment. So when you do the design, you will often start with the serviceability limit state or settlement. And really you need some sort of soil structure interaction model to correctly model the interfaces and the movement of soil and column past each other, which, as already one of the questioners asked, how do you do this? I think it's difficult to do with absolute certainty. We will talk about the axisymmetric link cell model, which we can use to do our design, but we should also be considering other methods. We obviously need to make sure the inclusion won't fail geotechnically, and we need to be aware that if we install columns with too high a factor of safety, they may actually present a hard spot at formation level, which could be problematic. So we're looking for very much a sweet spot in the design. We've also got to make sure the structural capacity of the piles, the columns, is adequate. Obviously, we're going to have axial loads, which may just be based on the plain cross-sectional area of the column, but we may need to consider buckling, particularly if we're through very soft soils. And at the edges of the system, particularly with embankments, there will be lateral loads. And they can be lateral loads applied from foundations. And then we obviously need to ensure that we've got I've called it concrete durability, but obviously if it was steel tubes, it would be the steel tube durability. So there's a lot to consider within the design. So how might we do this? Well, an example design approach is obviously you start with building a ground model, and then you need your loading conditions, and you need to know the geometry of the problem. What's the ground level now? What will it be? And what the construction sequence will be. Then you'll probably decide on your installation method, and you'll probably begin to have an idea of the sort of diameter of the column, because you'll know what tooling you've got. Now I'm going to introduce two terms, domain 1 and domain 2, which comes from the PSCE document. And domain 1 is where a column or the rigid inclusion system is needed to increase the bearing capacity. And that's a more onerous situation, and one that requires additional checks compared to if we're just looking to control settlement only. In other words, the ground is strong enough to support whatever we're putting on it, but the settlements are not. And that's called the domain 2. Okay, and as I go through this example, for simplicity, I'm just going to consider a sort of domain 2 type situation, but you can look at the PSCE document if you want to know about how to do the checks for domain 1. Now, for the domain 2, typically people these days are using finite element analyses, and they're using an axisymmetric unit cell formulation. And you can then adjust in your model your diameter, your length, the spacing, and the LTP geometry and parameters to get the settlement control that you're looking for. Once you've done that, you've got a feel now of the geometry of the problem. You need to go through and check the different components or elements of the system to make sure that they have adequate ultimate limit state capacity. So the strength of the inclusion, structural strength, the bearing capacity of the column at the toe, much like you would consider in a pile. You've got to consider the LTP design, bearing capacity of that, and its settlement characteristics. Okay. So you need to consider then all of these aspects to validate your overall settlement control will be satisfactory. You've then also got to do your foundation design, particularly floor slab design, and I'll come on to that a bit more in a minute. And of course, you may have geogrids in the load transfer platform as well. But as I've just said, this is just a domain 2 suggested approach. For domain 1, you will need to be looking at bending, shear, and bearing capacity of the column, improved ground. So you can see the series in more details. So here we have an actual example. This was a warehouse that was to be built, the new one. We're going to apply 100 kilopascal slab loading on the surface of the slab. So we have the slab loading, we have the slab self-weight, and for the rigid inclusions, we were looking at a rotary displacements helical system. So we were using a 450mm diameter column for the geotechnical design elements, but because we weren't as a matter of caution, we took for the structural check of the column just the central core Kelly-bar diameter, which was 30mm in this case. And the spacing in this case turned out to be 2 meters center to center on the square grid. So we had done our ground investigation, and this basically had shown there was an upper layer of firm to stiff clay, some loose to medium dense sand, but then this zone here of it was about 2.5 meters of very soft clay. These are all of the cone penetration test QC data plotted on one plot. We then went into some very stiff clay. This was a glacial boulder clay. This was a soft lake deposit. This was probably alluvium or lake deposit with a crust. Down here we had stiff clay, and then we very rapidly went into sandstone at about 9.5 meters. So the issue was concerns over the compression of this soft clay, hence the need for ground improvement. So I've talked about the axisymmetric unit cell. So this is how we went about doing the design here. Now, the concept of the unit cell is that if you consider you have a grid of columns and you take a column that is in the middle of that grid, it has that column is essentially working with the ground in this area to take the loads applied to it. And there's a kind of like a 3D formulation of that. Now, what we would then do, we would transform the area, the tributary area there, to an equivalent circle, or circle of equivalent area. And then we can use fairly readily in our finite element model the axisymmetric formulation. So we're only considering what's going on in one plane. You know, it's not a true 3D analysis. Now, this is okay, and it works reasonably well as a methodology for columns in the middle of groups of columns. When you get to the outsides, you may need to do something else because you don't have that support from additional columns on the outside. But anyway, so this is a good place to start. So we've got now our model built. We've got the column that's in there. This is the soil stratigraphy shown there. So let me just look at that. Okay, so we've got the, I think it's some furnished clay. the loose medium dense sand, the very soft material, the firm to stiff glacial till, and then we had sandstone down at that level. Now, you need to be aware, and you're obviously going to model within the FE the construction sequence. And in this case, you can see that we've got this is the natural ground surface. There was I think it was a oh no, there it was. Okay, yeah. Okay, so this was the natural ground surface. The dark green was the working platform which was used to support the rig, and it was 325 thick. And what happens is the rig comes in, it installs the column from ground level, but then before the concrete is cured, they come along and dig out this top bit and then recompact it same density as this material. So that was put in, and then what they called in this case a sub-base material, which is a continuation of load transfer platform, was built above that. Okay, and then above that it was the slab, and then the loading was applied. Now we put that into the simulation, run the calculations, and this is an output showing the calculated displacements going on within the ground here and the column here. And the displacement of the taken a center line down the column. Now, bearing in mind the column is terminated below the underside of the slab, and this is granular material. So you've got some compression of the granular material, very little compression of the column because it's rigid, and then some compression of the toe of the column down to the rigid sandstone layer. And that is the settlement of the column there. Now, on the outside, we've just got settlement of the ground, and these are contours of the ground settlement. So the ground settles much more than the column over this area. Settlements diminish until you get to the point where the column and the ground are settling the same amount. So this is where your negative skin friction is happening. This is your neutral axis. And below that, the settlement of the column now is greater than the settlement of the ground out here. So you're getting load transferred from the column to the ground. And obviously you've got some bearing resistance at the toe of the column as well. And that pattern is exactly what series says that you should be, sort of pattern that you should be getting from your analysis. And of course, it's very much ground condition and specific to the job, to the exact detail of that, but the principle should always be like that. So if we now look at the loads in the rigid inclusion, so this is again rigid inclusion, top there, bottom there. At the very top, the inclusion is collecting somewhere around the order of 150 kilonewtons in direct load. The load then increases because of this differential settlement and down drag, negative skin friction type mechanism to the neutral axis. It then diminishes off through skin friction to the toe of the column, and at the toe of the column you've got an end bearing resistance of around about, I don't know what that would be, 130 kilonewtons or something. The shear stresses that come from the analysis, they're a bit jaggedy, but they show that you've got the column's attracting load there, and then the sense of the shear stress swaps at the neutral axis, and you're shedding load there. And in this case, we had 157 kilonewtons on the head of the column, but the maximum load in the column was 225 kilonewtons. Of course, we're designing the column structural capacity for that. So, yes, so this analysis is estimating the amount of settlement of the column. I would also say that it might be worth doing an additional separate, almost like a past settlement check, just to make sure that your finite element analysis is reasonable. You design the geotechnical capacity of the column much like you would a pile. So you're going to have a factor of safety here on this maximum load. And you're going to design the structural capacity of the column much like an unreinforced pile. Now, when we look at the LTP, we have to consider the arching and the load transfer between the columns and the ground. Sorry, the load transfer in the ground between the columns, because we're getting load transfer into the ground there. We need to look at the LTP bearing capacity, which I'll come to in a minute. Now, a couple of really important things to note is that when we've got a floor slab, it has a major effect in spreading loads to column heads, okay, and reducing settlement between columns. But it is not a uniform stiffness at subgrade, and the slab must be designed to be compatible with the rigid inclusion scheme, okay? And the other thing to note is this axisymmetric simulation is it can't model variation in the load on the slab. You know, you can only model a UDL load, and therefore, if you've got some parts of the slab loaded, some parts not, and this is usually in the remit of the slab designer, they must really be aware that the rigid inclusion design is not the same thing as their slab design. So you've really got to make sure the slab designer is designing for a rigid inclusion system. Okay. I'll just slip on because time's going on. So the LTP design. Now, as we've seen, the LTP is above the head of the column, and as the load comes on, we've got sort of an upside down bearing capacity type problem. Providing this material is thick enough, you can have your Prandtl failure curve can be set up where the column is punching that way, and the resistance to a bearing capacity failure emerging within the column is a function of the resistance of the ground there and the load within the column there. And you can look at it in this way, and you will need to know obviously what the load in the column is, TP. You need to know what the load in the soil is, or the pressure in the soil, QS, which you can determine from either closed form equations, which are in a series, and will come from your finite element analysis. And you'll of course know spacing of column, diameter, and thickness of the LTP and subgrade stiffness. So you can use that as a means of determining your bearing capacity of your LTP. In terms of looking at the load shed, you can also use a conical formulation, and again I'll direct you to a series to use that to come up with what your head load in the column is for your bearing capacity check. Your FE model should give similar values of forces as you get from the closed form solutions, which are in series. Okay. If they're wildly different, then you really should be trying to find out why. Now, you might say, well, the load transfer platform may not be thick enough to generate this fall failure. And that's quite correct. And probably, if you're under a slab, won't be. But actually, it turns out that if the slab is closer to the head of the column, that the resistance will be greater than if you have the full depth and this full curve could emerge. And that's what is covered in the series line. Okay. Yeah, I won't dwell on that. I will dwell on a couple of points though, and that is, I call them embankments, and you've got to make sure that if you are not supporting on a slab or a foundation, that your thickness of material above the head of the column is adequate and it's greater than what they call this critical thickness. The critical thickness essentially is the thickness required to ensure that you've got a full collection of the load applied above the top of the column. Okay, if you've got this situation here with a thin load transfer platform and no slab, you can get settlement between the columns, which is what's happening here. Okay. I'm going to skip these parts because they're not very helpful. So in summary then, for this example, as I said, we had columns at 2 meter square centers. The settlement we were calculating was 23 millimeters under the applied load. The load in the head of the columns, 157 kilonewtons, and the maximum load was 225 kilonewtons. So we had about 68 kilonewtons of negative skin friction. And the base of the column was designed to have a factor of safety of 2 on the geotechnical capacity. Okay. So to summarize, design, we've just gone through very quickly, giving sort of flavor of the principles, but it's a 3D system, but you can make these simplifications. But the design can become quite complex and time consuming, particularly if you start taking into account edge effects and lateral loading. Actual national published standards don't, I think, adequately cover the design. So I would say the ASERI document is a good place to start, but hopefully this will improve in the next coming years, certainly with the Eurocode and maybe other codes coming out as well. Because of the complexity of the interaction between the components of the system, it's often very much an iterative design process. And whilst the unit cell approach can be used, as I say, that there are other complexities which should be considered within the design, but we haven't got time to go into today. And the final point is related to the actually previous slide here, that in this case, we had varying ground conditions over this particular warehouse. But what you can do, and again, it's a simplification, rather than going to a full 3D finite element analysis, which would be hugely complex and time consuming, you can do a series of unit cell calculations to essentially get what I would call a homogenized stiffness. In other words, the composite stiffness of the column and the ground in the unit cell. And then you can apply that to zones within your overall footprint and get a settlement profile for your whole building. That is what is meant by you can homogenize your 2D, it's actually symmetric really, into a 2D plane strain or 3D settlement analysis. Yeah, doesn't completely capture the full mechanisms at work, but does enable you to progress. Okay, now I've got a few other examples, but are there any questions there at this point? I have rattled through that very quickly.
Dr. Egan, I have a bunch of questions. So how long you will take to finish it? Then we can finish the questions all together.
Okay. So this is an example of a project where there were different size footings. So we did the unit cell model, and this is what I mean about the homogenization. So this is the unit cell model to get an overall sort of stiffness response. But then we looked at it in a 2D plane strain approach as well. Doesn't fully capture the 3D nature of the problem, but is very useful in considering interaction on footings, and particularly where footings are close together. This is another interesting project. This was where, and this saved an awful lot of money. This was a pond of pitch, of liquid tar, highly compressible material, no strength whatsoever for about 8 meters. And the structure that was going on was mostly isolated footings, and they had to try and limit settlement to 25 millimeters. So typical ground improvement solutions just wouldn't have worked because this was virtually a liquid. And therefore, piling had been proposed, and they were very large, or relatively large diameter piles, 600 millimeters, 10 to 12 meters length, and there are about 6,500 of them. So an alternative solution was to use precast concrete rigid inclusions. Now, the scheme summary was that that turned out to require 9,500 columns, which were the precast sections, but they were much shorter length. So those are the tops of the precast piles before they were broken off. And what was interesting, although it seems on the face of it there's a lot more work, greatly more, 50% more columns, much less in terms of total meterage of concrete used. And spin-off from this was obviously much less CO2. So there was not only a saving in cost, there was also a saving in the environmental impact. This is another one where vibrating tubes were used. The initial solution that had been proposed for this situation, where there were very soft soils down to about 15, 16 meters, was board piles, 800 millimeters diameter, 37 meters long. Okay. In the end, the alternative was able to use 500 millimeter diameter columns, 18, 19 meters long, spaced at 2 meter centers. The installation, as I say, was a vibrated tube. So it's just a plain tube with an end cap. The tube is placed over the end cap, driven into the ground or vibrated into the ground. Concrete is then introduced into the tube. The tube is withdrawn. The end cap stays in the ground as sacrificial, but that then generates your column. And it's again a low spoil solution and quick to implement. So I'm just wanting now to change the topic a little bit to specification and validation, and come back to my previous point, which was that it can often be different entities, different companies doing different parts of the design and implementation. So you've obviously got the ground improvement, and you need to be able to specify for the project's benefit the ground improvement system. So there needs to be some sort of, I would call it probably a performance specification setting out what the ground improvement, or in this case, rigid inclusions, must achieve. And that is probably going to have to be written by the lead designer. They're going to give the loads, the settlement criteria, and there may be limitations or criteria relating to size of column, spacing of column, etc. Then there's got to be the calculations to demonstrate the rigid inclusion system is going to work. And that's obviously going to be by the rigid inclusion designer, which might be an independent consultant or might be the specialist contractor. But then there's also going to be, or should be, a construction specification covering the quality of materials and methods to be used. And that is probably by the lead designer. So this specification here and this one here is probably by the lead designer. And then later on, once the columns are in, and we've had some questions about this already, the system needs to be validated. It might be that the rigid inclusion contractor will do that, or the lead designer might do that, or the rigid inclusion designer. But it's really important that the system is validated. So if we look at a performance specification, so this should include things like design life, temporary or permanent, design standards, if we're using a design standard, if there's one available, or something like a series, should be ensuring that the factors of safety, the different components are indicated, and it should also give the loading and any variation of loading that is applied to the ground improvement system. Okay. Issues related to the loading on the slab, if you're supporting slab, should be clearly understood as well. And if it's embankments as well, you've got to consider the lateral loading effects on the edges. Okay. So these are the sorts of things that should be in the performance specification. It should also cover settlement, which is total and differential. And if there are any geometrical or level requirements, for example, top of the platform, the underside of foundations, is there going to be any cut and fill of the pre-existing ground profile? And do bearing in mind that if you've got compressible ground and the ground is filled up before the rigid inclusions are installed, you could be generating additional loads and settlements at the new ground surface and within the columns, compared to if you've just installing at natural ground level or excavated ground level. Construction sequence is also needs to be known. So these are the sorts of things that need to be put in the what I would call performance specification upfront by the lead designer. Then once the design for the rigid inclusions is started to comply with that specification, the design checks, as we've discussed, need to be considering the serviceability limit state conditions, settlements of slabs, differential settlements, if applicable. You may need to consider stratigraphy changes where applicable. If there has been upfilling of the ground, you may need to consider the ongoing settlement that upfilling is generated. It's not just the new loads that are going to generate settlement within the ground. It's going to be the old upfilling. You need to consider the compression of the load transfer platform, the settlement of the rigid inclusion itself, and also consider any differential settlement or subgrade stiffness variation between where the column is and the space between columns. The ultimate limit state check should also be run, which is the bearing resistance of the load transfer platform, the punching resistance of the head into that, which is kind of linked to that, the maximum load in the column, the structural capacity and the bearing capacity. All of those obviously have to be checked. And there are other things as well that you may need to consider. You may need a working platform to support the rig. Now that working platform may double or may be reused or considered as the load transfer platform, but the design needs to be specifying the material type and checking the durability, strength, stiffness, and variations in thickness of that load transfer platform. That all comes out of the design as well. Yeah, that just covers the conclusion today. Now, this is where the big risks are, I think, with this system. It's often different contractors, or it could be different designers involved in constructing the system. Okay, so you do have this big risk of split responsibilities, and that has to be managed. And the best person to manage that is somebody who's probably higher up in their organizational chain than the specialist contractor. Okay. So the other thing that I think the lead designer should be doing is determining if there are any other constraints on materials and methods. Methods, thinking of noise, vibration limits. What instrumentation of the rig should there be? If you're doing a rotary displacement, you should be able to get or ensuring that you're getting some sort of computer readout of penetration, torque, crowd force, and definitely the placement of the concrete in the ground. That is a really important quality control check. And obviously the length of the columns to make sure that they are terminating in ground that is suitably strong to support them. Protection of the columns. So if the columns are installed and the specialist contractor goes away, it may be the general groundwork contractor or the main civil engineering contractor who then comes on and has to recompact the load transfer platform and place the slab. Now they've got to protect the columns so they don't get broken at that point. You've obviously got slab construction, which needs to be compatible with the ridge intelligence system, as we've discussed, and edge loading effects. Yes, because you've got the columns in the ground that have nowhere of at least one failure, where next to the grid of columns, a large stockpile was built, which failed, breaking a lot of columns. And I keep going on about the slab design. The rigid inclusions do not provide uniform coefficient of subgrade reaction. Yeah, it's stiffer over the head than between, and therefore the slab design must be compatible and must consider this variation here also when you're considering where the construction and movement joints are going and where uniform non-uniform slab loading is likely, which is in reality probably in most cases. Okay, and this just illustrates how you've got difference in subgrade reaction between the columns and in the area of the column. Okay. Now the testing of the columns. Firstly, you might have some preliminary or sacrificial testing of columns, where you're going to test them to geotechnical failure. And then you may have some working tests. So that's all columns that you're going to incorporate in the project. You're going to be doing these as you're going along, when you're constructing the works. And you might test 1.25 to 1.5 times whatever their working load is. Now, when you're load testing the inclusions and doing the preliminary or sacrificial testing, it's not unusual to do some long columns, which are the design length, and do some short columns that are just within the soft ground. Now, the purpose of these columns is to try and assess what the soil to concrete shear stress is going to be in the zone of negative skin friction. Okay, they could be very valuable. And then your long column, when you test that, you've got to allow for the working load that's going to be applied, and you've got to then add on to your load in the test the resistance that's been generated within the test over the negative skin friction length to ensure you really are testing the bottom of the column to the maximum it can be exposed, maximum load it can be exposed to. In terms of working tests, the suggestions can be anywhere between you do one working test per 100 columns if you've got just a few columns, but you may do a fewer proportion of tests. You know, once you get above about 400 or 500 columns, you may do 1 in 200, 1 in 300, something like that. Of course, when you do the test, you've got to accurately measure your load and displacement. You'll also be doing material tests, and you may expose columns, measure diameter, and test the head quality and integrity, and check the load transfer platform thickness. These individual tests are more like a pile test, or can even be done with a plate loading test type setup, where you expose the top of the head and just put a plate on it and put the load on, because usually the load in the column is not going to be high, you know, maybe 100, 200 kilonewtons. What's that? Maybe at 20 tons, and you can use a rig on site as the reaction. You may want to test a number of columns, so you may do something called a zone test. Now, the thing with that, you're going to need quite a lot of Kent ledge, so the test plate is in there, but you've got to have all this Kent ledge to provide the reaction, and it would spread over a number of columns. Okay, and of course, what you're doing here, if you just do a little plate load test on the surface, you've only got a small zone of ground that you're loading. So the one reason for doing the zone test is that you're testing much greater depth of the ground, and you are approaching the conditions that the column and the ground will feel when actually in use. You may need to do these tests for quite a long duration to allow for any settlement effects to come out of the ground, for consolidation to happen. You also need to be testing the load transfer platform between columns. Of course, you want the material certificates and knowledge of that material. You want to make sure the material is compacted adequately, and therefore just some standard plate tests can be good for that. And you might do some other just validation checks, checking thickness and ensuring the head preparation and compaction over the column head is correct, and the column heads are either not being cut off too high or cut off too low. Okay, so in summary, so that pretty much concludes talk. So the summary is that rigid inclusions have been under development for 50 years or more. They are increasing. Computer design methods, finite element methods certainly have supported the development, but need to be used with appropriate caution. I think we have reached this tipping point in many countries, and we will see more and more inclusions being used. but there are risks with the technique that need to be managed. They can be installed by readily available plant if you've got piling rigs or ground improvement rigs. You've got the kit to do it. You may need some tooling, but that's relatively easily obtainable. And the system is challenging traditional piling and ground improvement on some projects, without a doubt. So it is certainly an emerging technology. But do be careful again where there is split responsibility in design and or construction. Okay, so that is that. Very happy to take more questions, Tahir.
Thank you very much, Dr. Egan. Let me tell the audience that's up till now, I have 17 questions. Oh. And I will struggle to take all these questions during the time I have left with, but I'll try to take all the questions, and I'll request Dr. Egan to, wherever it's possible, I know it's a huge subject, it's not easy to answer briefly, but wherever he could help me to cut down the time, so please do so. So the first question is from Mr. Nadeem, Engineer Nadeem. He's asking, how could we assess the increase in strength after rigid inclusion?
Increasing strength of the ground. Okay, so this would imply that you are in what I call domain 1, when you are using the rigid inclusions to increase the bearing capacity under a footing, and you do that using a sort of a modified bearing capacity type calculation. But that includes the need to look at the lateral loading effects that you would get from a sort of a bearing capacity shape type failure. And if you want to do that, I would recommend you look in the ASERI document that covers, and it provides several methods for doing that, which are quite complex.
Okay. The next question is from Suhail Kibriya. He's asking, how much is this system cheaper than piles?
It could be 2/3 the cost of that sort of order.
Okay, thank you. And the third question is from Engineer Shahzeb. It's a pretty long question. As we move towards more complex urban environments and underground infrastructure, how adaptable is rigid inclusion technology to varying soil types and geologic conditions? And what are the key considerations for successful implementation in urban settings? I think the question has already been answered, but if you want to answer it quickly, please do so.
Okay, I think with any ground improvement technique, you need the right ground conditions. So soft ground, but a good founding strata. In urban situations, noise, vibration are going to be key issues. So you've got to be able to construct silently and without vibrating too much, which actually the rotary displacement system is quite a good system.
Haziq Zahir is asking, do we not even provide minimum reinforcement in the rigid inclusions column, unlike piles? I think reinforcement is not required at all. Yeah.
Yeah, they can be completely unreinforced.
Correct. Now, this is the fifth question from Engineer Nadeem. He is asking, we use timber small piles in our few projects and then loaded with sand and gravel mixed layer, and it works very well for very soft soils. You have to say anything on it?
No, a great example of something that's not concrete.
Yeah, exactly. Suhail Kibriya is asking, will a rigid inclusion to be akin to a micropile if its upper part is reinforced and connected to the structure?
If you're connecting it to the structure, then it's a pile.
Okay. There's another question from Suhail, seventh question. It is from Suhail Kibriya. Has some instrumented loading of the ground has been attempted to resolve the complex load transfer paradox?
Yes, there's a lot of research has been done. And again, good place to start is the PSCE document, but there are lots of other more recently published papers as well.
Okay, next is from Muazzam Nawaz. He is asking, in Pakistan, a developing country where implementation of the subject ground improvement technique applicable in residential of office buildings and roads. I couldn't guess what is the question. Did you understand anything out of it? I didn't.
No, but it,
Okay,
as discussed before,
we'll
we
leave
could
it.
easily
We'll leave it.
do
We'll leave it.
Yeah.
Then it's
Yeah.
Nadeem. What is the behavior difference of rigid inclusion and sand columns? Behavior difference of rigid inclusion and sand columns, basically.
Yeah. The rigid inclusion is going to be a lot stiffer than the sand column. And the sand column, I suspect, is going to rely on lateral confinement from the ground, the host ground, which the rigid inclusion doesn't need.
Okay. Now we have the 10th question again from Sohail Kibriya. He's asking, what is the constitution of load transfer platform? I think you answered it somewhere in your...
It will be a clean granular material and compacted. Something you would use as a sub-base for a road, for example.
Okay. Next question is from Tatiana from Belarus. She is asking, are any settlements under RI tips?
Are there any settlement under the rigid inclusion tip?
Tips, yes.
Yeah, you mean the toe?
Yeah.
I presume. Yeah. So yes, the bottom of the rigid inclusion will settle, and you should consider the global settlement of the system where required. The example I showed the design on, there was sandstone very close to the tip, so there wasn't much settlement in the ground below. But yes, you should be checking that in where necessary.
Next question is from Mubashir Aziz. He's asking for bearing capacity of 0.5 tons per square foot to 0.75 tons per square foot for buildings, for building design. What are your recommendations for ground improvement of rigid inclusion?
So it's 0.5 ton per square foot. So I'd have to do a calculation. Even though I'm in the UK, I don't know what's that KPA. So it's probably about 9 times different, isn't it? With 5 tons. So what's that, about 50, 60 KPA? Is that correct?
It's half ton per square foot to 0.75 tons. It should be around.
Yeah. Yes, I think you can do that with rigid inclusions.
Yeah, exactly. He's asking, what are your recommendations for ground improvement for rigid inclusions? He's asking for your recommendation for such a low bearing pressure.
Yeah, it depends on the ground, doesn't it? It could be rigid inclusions, it could be stone columns.
Yeah, exactly. So next is Nadeem. He's asking for a floor having variation of loadings, how this system works.
Yes. You need to look at it very carefully. It depends on the magnitude of change of loading, but essentially you've got to consider it'll be a slab designer problem, I think, and you need to be considering your actual subgrade reaction across in a 3-dimensional situation.
Okay, next question is also from Nadeem. He's asking, if we have no margin of filling over the rigid inclusion, how this system will work?
So if you have no...
If we have no margin of filling over the rigid inclusion, how this system will work?
So you're saying that the foundation is straight onto the concrete? Yes, that is often, that is often done with isolated foundations. and that's perfectly acceptable as long as there is not a mechanical connection.
I have further few questions. This is from Haziq Zahir. He is asking, how do we perform the FEA, I think it's frame equivalent analysis, in the case of rigid inclusions with an averaged stiffness, since the stresses induced due to differential settlement vary throughout the depth of rigid inclusions?
Sorry, could you ask that again? I didn't quite.
Yeah, how do we perform the FEA in the case of rigid inclusions with an average stiffness, since the stresses induced due to differential settlement vary throughout the depth of rigid inclusions? Did you get the question?
Yeah, I think so. Is this on the homogenization concept? Well, yeah, if you use a homogenized analysis, which is probably going to be a plane strain type analysis, you're only picking up the general sort of macro performance, or you're only doing a macro simulation. You then need separately to be looking at the distribution of stresses within the ground and a rigid inclusion specifically. So they are two different types of analysis. And if you've got a really complex problem and you have to go to a three-dimensional analysis, then that's what you would have to do.
Okay. Now, the same gentleman, Haziq Zahir, is asking, can we anchor the slab to the rigid inclusions with a properly designed slab in order to avoid deformation of the slab?
You're defeating the whole object. If you're going to connect the slab to the inclusion, it becomes a pile slab.
Okay. Now we have a question from Nabil Ahmed. He's asking, how effective is the rigid inclusion system in order to mitigate the soil susceptible to liquefaction?
Yeah. You can use them for liquefaction or seismic situations, but you've got to be very, very careful in your design that they don't break, because they're quite brittle. And if you are going to get settlement of the material below an already constructed slab, you're probably going to get voids opening up between the columns. So you've got to consider that very carefully.
Okay, thank you. And now we have a question from Rizwan Mirza. He's also my co-host here. In the absence of only a few established and time-honored codes of practice on the subject, are there potential challenges in terms of handling professional liability suits for the designer?
Yeah, I think so. I think without there being formally published national standards, you are, I think as a designer, you can still design, but you've got to be very sure that the design is going to work in every situation. And I think the challenge comes when commercial pressures come on, and maybe clients have heard about rigid inclusions and they can save 30% over a pile solution, and you suddenly get pressurized into coming up with that rigid inclusion solution, and yet they don't want to or haven't got the time to do the necessary on-site testing to validate that the system is going to work. So I think as a designer, it might be the safer option to just say pile your structure. But as a responsible engineer considering things like sustainability, we're kind of we're kind of encouraged to think of these more innovative and more efficient systems. I don't know if that answers the question, but there are more risks.
Okay, thank you. Now, these were the questions which I had noted when you closed your presentation. I think after that, something has come more in the chat box also. Let me take few more questions. This is from Sohail Kibria. He's asking, time and cost are two important parameters. Where do you place rigid inclusion system amongst other contemporary methods?
I would say that, you know, it's going to be a quicker method in the right conditions compared to piling, and some of the savings are not in the ground or geotechnical work. They are in the savings in not having to break down piles and tie in reinforcement.
Now we have a question from Shahzeeb Khalid. It's again a bit long question. For infrastructure projects involving heavy loads or dynamic loads, such as highways, bridges, or industrial facilities, what design considerations or specifications should engineers keep in mind when incorporating rigid inclusion ground equipment into their plans?
Yeah, I think well, heavy loads, you're obviously going to have heavy loads in the system, so that you have to demonstrate the system can take that. And if the loads are too heavy, then you probably, you know, it's not appropriate to go for rigid inclusions. In terms of dynamic or cyclic loading, again, it can be a somewhat brittle system, and it might be, again, that if you have got significant dynamic or cyclic loading, that it wouldn't necessarily be the perfect solution. On the other side, you do have the load transfer platform, which will absorb some of that, you know, act as a cushion. But it depends exactly what the problem is.
Okay, now, is it a last question? Yeah, this is going to be the last question. Is there any standard test method for rigid inclusion systems like ASTM D1143 for the pilots?
No, not that I'm aware of. So you would, you know, for example, use a pile testing standard if you're doing a load test on the individual inclusion column.
Okay, now it is just a comment, and this is going to be the last one. This is from Ibrahim Al-Taruti. I hope I have pronounced it correctly. If I did not, I tender my apology. Dr. Egan, he's saying excellent presentation. What would be okay, this is a question also attached. What would be the typical properties of the concrete using in rigid inclusions?
Yeah, you can often go for a slightly lower strength than you would accept for a pile, maybe down even into a 12 or 15 Newton per millimeter squared compressive strength.
Okay, thank you very much. Now, question answer session is concluded. Now, I will ask my co-host, Rizwan Mirza, if he wants to say something. So, Rizwan, please be brief and go ahead.
Dr. Egan, I think it was a wonderful lecture. I must say that it's not a formal statement. I'm saying it from the core of my heart. It was an honor, and I'm confident that everybody, junior or senior, experienced or a novice, have learned. I personally have greatly learned and benefited from your lecture. We would hope to see you again and again on our platform. It's a matter of great honor for us. And by the way, we have one of the largest level of participation today. That speaks volumes about your goodwill that you have generated through your past lecture. Thank you very much.
Well, thank you, and thank you for the invitation. And it is a great pleasure to present to you, and I feel honoured also. Thank you.
Okay, thank you, Rizwan. Dr. Egan, frankly speaking, I am speechless. I don't know how to thank you, but it's my duty to thank the guest speaker in the end for your enlightening discussion on rigid inclusions. Your systematic presentation and clear slides have undoubtedly enriched our understanding of rigid solutions. We appreciate your insightful contribution to today's session. And I would also like to say that this complicated subject you have explained in a very simple way. I think even the young engineers who are present here, they must have understood it very well. So as Rizwan said, that we had a very large audience today. I think the maximum we ever had, and it made my job very difficult to handle so many people. And anyhow, thank you very much, Doctor. It was a wonderful session, and we had a lot of stuff to learn about. Anyhow, now we have to conclude this session. So let me make some announcements, then we will conclude it. The next lecture, number 65, will take place on 20th April 2024. The topic is geotechnical aspects of earthquake engineering, and our guest speaker would be engineer Naimur Rahman Durrani. Those who have registered here for the certificates, CPD, they will get their, they can start collecting their certificates from 15th of March, and that will be, that is not 15th of March, I'm sorry, I have to check. That is coming Thursday. From coming Thursday, you can start collecting your certificates, and the address is same, 14A1 Block P, Model Town Extension, Lahore. And before coming, who wants to check whether the certificate is ready or not, they can contact Ahmad Akram, and his cell number is 0347-462-5111. I again repeat, the person to contact with is Ahmad Akram, and his telephone cell number is 0347-462-5111. And I must tell everybody that Dr. Egan is also the associate of Pakistan Society of Civil Engineers, and we are honored for his acceptance of his associateship with Pakistan Society of Civil Engineers. We are really proud of you, Doctor. Now, before I conclude, I want to express my heartfelt appreciation for Sadia Naveed and Hasnan, whose tireless efforts behind the scenes have contributed significantly to the quality and seamless execution of this live transmission. As we approach the sacred month of Ramadan, I extend my warmest wishes to all of you. May Allah bestow His abundant blessings upon you throughout this auspicious time. Inshallah, we look forward to reconnecting with you on April 20th, 2024. And Dr. Egan, you will get your shield and your certificate by DHL, I think, in 2 weeks' time from now. So thank you very much for attending this session, and may Allah bless you all. Thank you, Dr. Egan. Bye-bye.
Thank you. Bye-bye.